Welcome everybody, my name is Andrea Maioli and I am a first year PhD candidate at Politecnico di Milano in Italy. Today we present you a new program design pattern for the batteryless devices of the Internet of Things, and I will show you how to use such design pattern to lower their energy consumption. The devices of the Internet of Things are powered only using batteries, which must be periodically recharged, replaced and disposed. This introduces a significant environmental impact, and for this reason, researchers want to replace batteries with energy harvesting technologies. Here, devices use the energy harvested from the environment as the only power source, which is then stored inside a capacitor that acts as an energy buffer. Unfortunately, using such constrained energy source causes devices to compute intermittently. So, the device is initially powered off and harvests energy to recharge its capacitor. When it has sufficient energy, it powers on and starts computing until it empties its energy buffer. Here, the device immediately shuts down and loses all the computation achieved. As a consequence, in the next power cycle, the device will have to restart the computation all over again. This clearly harms program forward progress, as devices cannot complete their programs. To overcome this problem, during the computation, the device pauses the program execution and saves a copy of its volatile state into a non-volatile memory location, which is persistent across power failures. This copy is called checkpoint and includes the program counter, the stack pointer, the register file, and the main memory. Then, when the device restarts after a power failures, it restores the checkpoint and resumes the computation from where it stopped. Unfortunately, checkpoint operations introduce an energy and computational overhead that are proportional to the size of the data they save, as this energy could be used for the normal computation. To reduce such overhead, mixed volatile systems allocate portions of the main memory into their internal and directly addressable non-volatile memories. These portions could be either single variables or entire memory sections. However, this causes an unexpected behavior recognized in the literature as intermittence anomalies. So let us consider the execution of this program where variable a is directly allocated into non-volatile memory. We save a checkpoint, which does not include a, since it is already non-volatile, and from now on, we basically increment a by 1. So we set b equal to 0, which is the value of variable a, we increment b to 1, and then we update a to 1. Now a power failure happens. When a device has enough energy to restart the computation, it restores the checkpoint but not a, since it was not saved during the checkpoint. We must consider that variable a had a value of 0 during the checkpoint, but now it has a value of 1. This is because, as it is non-volatile, it retained the effect that line 4 produced during the previous power cycle. Now, we resume the computation from line 2, and this is where the intermittence anomaly happens. In fact, line 2 accesses a value variable a that was produced during the previous power cycle by a future operation, that is line 4. For this reason, at the end of the execution of line 4, variable a is instead updated to 2, and these results differ from the one we would obtain with an equivalent continuous execution of this same code, which would bring to having a equal to 1. So this clearly represents an unexpected behavior which may harm result correctness. The problem is that not all the intermittence anomalies are undesirable. However, all the existing solutions avoid all the intermittence anomalies, and for doing so, they usually place additional checkpoints, which significantly increase the energy overhead that checkpoint operations already introduce. Moreover, these solutions also limit developers' possibilities, as they enforce an execution to be equivalent to a continuous one. Our solution consists in taking an opposite direction. We intentionally allow the occurrence of specific intermittence anomalies to unlock a new program design pattern, which we call intermittence awareness. Intermittence awareness allows developers to consider intermittence as a new input for their programs. This then allows developers to react to power failure by tuning the program control flow or the program data flow accordingly to their requirements. Here we show an example where we use intermittence awareness to track the number of power failures. We then use this information to avoid the re-execution of a portion of code. So let us consider the execution of the following program where variable r is non-volatile. We initialize r to -1 and then we save a checkpoint, which does not include r since it is already non-volatile. Then we execute line 2, which increments r to 0. Now we execute line 3. The if condition evaluates to true, as r is lower than 1, and thus we execute line 4, which sends some information to another device. Now a power failure happens. When the device has enough energy to restart the computation, it restores the checkpoint but not r, since it was not included in the checkpoint. Here we can notice that the value of the non-volatile variable r differs from when the checkpoint was saved, as r retained the effects that were produced during the previous power cycle. The computation resumes from line 2, which increments r to 1. Note that here we have an intermittence anomaly. However, we are allowing its occurrence so to enable R to track the number of power failures occurred since the checkpoint. Then we execute line 3. Conversely to the previous power cycle, the if condition now evaluates to false as R is no longer lower than 1. Thus, we skip the re-execution of line 4, and we avoid signaling the same information another time. This would not be possible without allowing the occurrence of an intermittence anomaly, which is the core of the intermittence awareness design pattern. Note that this represents an intuitive explanation of the intermittence awareness design pattern, and this is only one of the many possibilities that intermittence awareness unlocks. To make this concept concrete, and to show other applications for intermittence awareness, we design a technique that exploits this new design pattern to reduce checkpoint overhead inside loops. Here, we target any static checkpoint mechanism that plays checkpoint calls inside the program at compile time. When a power failure happens, the program resumes from where the latest checkpoint was saved. This means that to preserve the computation done inside loops, we need to save a checkpoint at the end of each loop iteration. Otherwise, a power failure would cause the program to resume the computation from a checkpoint that is before the loop. As a consequence, the entire loop would be recomputed from the first iteration. This means that all the computation achieved inside the loop during the previous power cycle would be lost. However, placing a checkpoint inside the loop body introduces a significant energy overhead, as checkpoints are now executed at each loop iteration. We use intermittence awareness to reduce such overhead, so let us focus on this program where the loop iterator I and the result vector res are non-volatile. Note that also there is no checkpoint inside the loop body. We save the checkpoint of line 3 and then we enter the loop. We continue the computation until we reach the third loop iteration, and then a power failure happens. When the device has enough energy to restart the computation, we restore the checkpoint and we resume from line 4, which is the loop. Here, we allow the occurrence of a sequence of intermittence anomalies. Since the loop iterator I is non-volatile, it retains the effects that were produced during the previous power cycle, and thus the loop reads the loop iterator I and resumes from the third loop iteration. Moreover, we can also notice that the result vector contains all the results of all the previous loop iterations, which were computed during the previous power cycle. This means that with intermittence awareness, we were able to preserve the computation done inside the loop without requiring a checkpoint inside the loop body. This situation would not be possible if we do not allow the occurrence of the intermittence anomaly. To apply our loop instrumentation technique, we design and implement Lapsus. Lapsus is a programming abstraction that exposes a set of macros that allow developers to apply our loop instrumentation technique to any program. The macros are extensively described in the paper. The effects of applying Lapsus macros are mainly four. First, we identify the minimum amount of data that requires to be preserved across power failures, which we call loop state set, and Lapsus allocates it into non-volatile memory. The loop state set includes the loop iterator, which in the previous example was variable I, and all the variables that carries the loop intermediate and final results, which in the previous example was variable res. Then, Lapsus removes all the checkpoints that are present inside the loop body, as they are no longer required, and it also ensures that a checkpoint is placed before the loop, so to fix where the computation resumes after a power failure. Finally, Lapsus moves the initialization of the loop iterator before the checkpoint that it has outside the loop, so that the loop iterator is not reinitialized every time the computation resumes after a power failure. And this is the final result. We evaluate Lapsus performance in its worst case scenarios. We use as baseline a generic trigger-based checkpoint mechanism, which we call trigger, and which has the same behavior of existing trigger-based checkpoint mechanisms such as harvest and mementos. At each checkpoint trigger call, trigger decides whether to save a checkpoint or not depending on the level of the energy buffer. As benchmarks, we use an heterogeneous set of applications that are commonly used in this domain. So we use the cyclic redundancy check that is commonly used for data integrity, the fast Fourier transform that is commonly used for signal analysis, and the Dijkstra algorithm that is commonly used for finding the shortest path between the nodes in a graph. We consider as target microcontroller unit the MSP430FR5969 from Texas Instruments, which features a directly addressable and internal ferroelectric RAM. We use the default compiler optimizations, and we consider a clock frequency of both 8 and 16 MHz. We consider these two frequencies because the non-volatile memory performance depends on the MCU frequency. Then we model the clock cycles and the energy consumption of the MCU, and we evaluate the energy and execution time overhead that both Lapsus and Trigger introduce with respect to an uninstrumented program. We report in the following slides the most interesting results, and we clearly provide a more extensive evaluation in the paper. So first, we consider the overhead that Lapsus and Trigger introduce with respect to a single loop iteration. At each loop iteration, Lapsus non-volatile memory accesses consume 24% more energy than Trigger calls that do not save a checkpoint. However, as Trigger needs to query the ADC to verify the level of the energy buffer, it has a 37% higher execution time than Lapsus. Moreover, these devices experience frequent power failures, and in this scenario, Trigger calls save a checkpoint. In this case, on average, Lapsus has a 35.2 times lower energy consumption and a 48.4 times lower execution time than the Trigger complete checkpoint operations. We then evaluate Lapsus and Trigger energy overhead in the presence of power failures with respect to a complete execution of the loop. We consider a frequency of power failures in the range between 0 and 10%. This indicates the portion of loop iterations that end up in a power failure. Note that this also indicates the number of trigger calls that end up saving a checkpoint, as Trigger executes a trigger call at the end of each loop iteration. In the CRC benchmark, Lapsus has always a lower energy consumption than Trigger, as here, trigger calls introduce a higher overhead than complete checkpoint operations and non-volatile memory accesses. Instead, in the FFT and Dijkstra benchmarks, Trigger has a lower energy consumption with respect to Lapsus only when rare power failure happens. For example, the worst case happens in the Dijkstra benchmark at 16 MHz, where Trigger has a better energy consumption than Lapsus only when less than 1.58% of loop iterations end up with a power failure. In conclusion, we show that by allowing the occurrence of specific intermittence anomalies, we unlock a new program design pattern, which we call intermittence awareness. Intermittence awareness allows us to consider intermittence as a new program input and makes programs aware of the intermittence. We then demonstrate the potential of this design pattern with a loop instrumentation technique that reduces the energy required for preserving the computation achieved inside loops. Finally, we design and implement Lapsus, and we evaluate its performance, demonstrating not only the potential of this new concept, but also the possibilities that the intermittence awareness program design pattern unlocks. So, this ends my presentation. If you want to contact us, this is my email and our lab website. Thank you very much for your attention. I'm now ready to take your questions.